So in this diagram we see a dipole, very small, so we're looking at someplace far away from, kind of far away from the dipole, but still pretty close. And you can see the photons have this little warped view, this little bubble that's being pushed out from this dipole. And as the wave continues to travel, we call this the near field, which is close to the antenna. And once we get into what's called the far field, these packets have stretched out to the point where they look fairly straight in appearance. And so these are called plane waves. And these are the waves that we're normally getting when we listen to our radio and watch television. We're getting these plane waves. When you're into the near field, things become slightly unpredictable. The math is much harder to be able to deal with the intricacies of being so close to the site. Usually need computers to run these simulations. But when you get into the far field, it's much easier to calculate. I should say much easier to calculate, but something we don't have the background to do in this course. But these become much more useful in doing simulations because they're so predictable. Now, if we take and add multiple dipoles near each other, we can get what are called different antenna patterns or radiation patterns. So here we have, this would be probably one dipole. And if we were to look at it in 360 degrees, it looks like a donut shape. And if we put more dipoles together, we can create areas where the transmission of the electromagnetic waves is really good. So that would be like this section up here. But in this angle, we're not getting much. And this bottom angle, we're not getting much. We're getting quite a bit of radiation, electromagnetic waves from the center section and from down here at the bottom. So the strength is indicated by how far away from this central axis that we are. And notice that depending on the number of elements, you can get all sorts of different wave shapes. Some of these look similar, but if you notice that the one that's above is a little bit thicker here, and these sections are a little more rounded between the two. So it's just moving those dipoles a small amount. So you can create these patterns where electromagnetic waves are constructive and destructive interferences to create these patterns of electromagnetic energy that's being radiated from the antenna dipoles. Now, this is an emerging science antenna design. It's very big. There's a lot of new concepts that are coming out. One of them is that was developed takes one antenna and it makes it look like 5 separate antennas. Each of these antennas have these beams that come out. I didn't draw this very well. But there's 5 beams that come out. This was one of the early prototypes. Let's see if I can draw better here. And the antenna acted as if it was 5 separate antennas has some kind of a radiation pattern like this. This would be looking at the horizontal plane. This was called a 5-beam antenna. They also had a 9-beam. So pretty much looks like this, but you fit 9 of them in here. And then we had a 2x9 beam, which was 9 beams and then 2 rows of those, one on top of the other. So there's a lot of different configurations that you can do with these antennas, and it's a very large market for building these antennas to be able to provide service, especially in cellular systems. Now these antennas are not small. This antenna for 850 megahertz weighs about 250 pounds, and it's about 5.5 feet by 5.5 feet. The 9-beam antenna, and they're much larger, and they can weigh up to about 350 pounds. So these are the different kinds of antennas that are being used, and they're very useful. And if you ever want to get into the industry, antenna building industry, it is growing. It is a lot of math, much beyond what we do in this course, but it does have a lot of demand. So if you get a job with an antenna building company, you probably have a job for quite a long time.